Hello, everyone. There are a few more spots to the front here, if you want. I'm Julian. So today I'm going to talk about the Columnar roadmap. In particular, I'm going to talk about Apache Parquet and Apache Arrow. So full disclosure, I co-created Parquet while I was at Twitter. Currently, I'm an architect at Dremio, and we're building data analytics tools on top of a lot of open source work. And I've been involved in various Apache projects over the years. So today, we're going to talk about building community-driven standards around Parquet and Arrow. I'm going to introduce by explaining a little bit what are the benefits of columnar representation and why everyone's doing it. And then I'll talk in details about the better vertical integration between Parquet and Arrow, and then we'll tell you what that is, and Arrow-based communication. So first, I think the most important part of this is how to build a community. And because in open source, really the most important thing is not the source. I mean, it needs to be good quality, but the community around it is much more important, and that's what makes it successful and useful. So first, Parquet came from a common need for on-disk columnar representation, and it's inspired from a lot of work in academia and the Google Dremel paper. And, a lot of databases are using it, like Vertica, are using columnar representation to speed up analysis. Arrow is similar, coming from a common need for in-memory columnar. So if you look at papers like MonetDB, papers that are the beginning of vectorized execution, it's the next step in making SQL execution and all those things much faster. So Parquet, we started it. I started prototyping something at Twitter, and the Impala team at Cloudera was prototyping a columnar representation for Impala. And we started working together and merged our design, and they were coming more from the native code, C, C++, and I was coming more from the Java side, and we put our efforts together. And after that, more companies joined. Criteo, which is an ad optimization company, Netflix joined the effort. And before you knew it, it started being integrated in many of those projects. Spark SQL made it its default format. Drill made it its default format. Obviously, Impala, it's its default format, and started being integrated in everything, Hive, all those things. And so building on that success, on having done already the effort of building that community and have all those projects talk to each other and agree on how we're going to represent stats, how we're going to represent things to have a standard, because it's that much more valuable when we all use the same format and you have a lot of options to use for all those things. So building on that, we created Arrow, because all those projects were also looking at, well, the next step is vectorizing execution to make it 10 times faster, and so we need to come up with an in-memory columnar representation. And so to benefit everyone, we may as well come up with the same one and agree on it. So we started Apache Arrow as a top-level project, and it's involving people from all those projects on the PMC to make sure we first agreed on what we were doing, and then start building it and enable making it a standard for the ecosystem. So before, when you wanted to integrate things together, so we have on top, we have more SQL execution framework, and on the bottom, we have more like storage layers. And this is not exhaustive, right? This is to give you an idea. Then you need to figure out a way to find a common representation of data for each of those things, right? And they're all slightly different. They have different in-memory representation. Most often, nowadays, they use Parquet, but they built Drill or Impala, have their own optimized, vectorized reader, then integrate with they have. And so there's a lot of duplicate effort. And also, in many cases, like, for example, if we look at Spark and Python integration in PySpark, there's a lot of overhead of finding a common representation. Often it's the lowest common denominator, and there's a lot of overhead just serializing, deserializing data and converting it from one representation to the other. So thanks to Arrow, the goal is now if we agree on a common representation that is very efficient for doing data processing of many sorts, then we remove, first it's much more efficient, and second we remove all the overhead of converting that representation because it's already the native representation of a lot of those things. So there's very little cost of serialization. There's no cost of serialization, deserialization, and it's already much better representation for doing query execution, for example. So I'm going to talk a little bit about the columnar representation. So easy, right? So before we were doing rows, now we're doing columns. So columnar representation. So if you think of a table, so here you have a two-dimensional representation of a table. You have columns, you have rows, but really when we write a table to a computer on disk or something, we end up with a linear representation, right? We need to take those rows in a row-oriented format. You just put every row one after the other, right? First row, second row, and so on. And so you end up interleaving values from different types, from different columns. And most of the time, when you do a query, you actually query a subset of the columns. And so it's much more efficient to skip data you don't need when you put all the columns you want together. We have in columnar representation, we put one column after the other. And so when we select A, it's much faster to scan all the A's and skip everything else. And another benefit is because we encode multiple values that are of the same type instead of having strings, integers, date, and so on, for example. We have all the strings together, all the integers together, all the dates together. We can do encodings that are much more efficient and they compress much better. And so usually columnar representation compress much better than a row-oriented one. And so another question is, hey, look, you had Parquet as a columnar representation already. Why didn't you just put it in memory? Well, the thing is, there are different trade-offs. So when we store on disk, it's mainly storage. It's going to be written once and read many times and read from different point of views. We may access different columns with different filters. And there's a need for more compactness. And then we're optimizing more for scanning, doing scans really fast on this data. So there's like mostly streaming access. And so there's a priority to reducing I/O. We still want fast CPU, low CPU costs, but reducing I/O is more important. For in-memory, it's more transient. Usually it's been loaded in memory for a query in particular, even though you could do caching as well and keeping things around. But the data is more transient, and we want highest priorities to CPU throughput, right? So it still needs to be compact, but we'll favor making it fast rather than making it more compact because it's in memory, latency is lower, and you want to be able to have random access, to access something from its index in constant time. So if we look a little bit into Parquet, so both Arrow and Parquet support nested data structure. And Parquet is a compact format because it uses type-aware encodings. So you know it's a string, you know it's an integer. If you know it's an integer, you know the max value, you can use fewer bits, things like that. And you get better compression than just throwing general purpose brute force compression algorithm like gzip. So usually you don't want to use gzip. You can use LZO or Snappy or more modern Z-standard or Broadly. But just simple things, when you know the types, you can just write a simpler algorithm that would compress better and much faster because they don't have to just try to compress random bytes. They understand them better. And it optimizes I/O by doing projection pushdown, which is reading just the columns you need, and predicate pushdown, which is pushing the filters. So the nested representation is borrowed from the Google Dremel paper. And that's not what I'm talking about today. So if you want more information, go to that blog post. I'm going to share the slides as well. But basically, it's a generalization. Instead of using a bit, 0, it's null, 1, it's defined. like you do for a flat schema. You use a number which is 0 for its null, 1 is defined at the first level, 2 is defined at the second level, 3 is defined at the third level. So it's kind of recording where the null is in the tree of the schema. And same thing for repeated values like list. It will record at what level we're starting a new list when you have nested lists. And so it's still, the advantage is it's still very small integers you can store on a few bits, and small overhead, and it generalized to nested data structures. So to summarize, Parquet, with projection pushdown, you read only the columns you need. With predicate pushdown, you can narrow down to only the rows you need or fewer rows to an approximate. And so you minimize I/O to read only as little as you can. And so this slide is about more details about the Parquet representation. So this is your Parquet file, and it's columnar per row group, right? Because you want to be able to load one row group, which is a group of rows, in memory at once. So you split, inside the file, it splits in row groups to make each of them in a reasonable size that would fit in memory. And then it's each column, it's stored in column inside of it. So each of those columns is one after the other. And inside a column, we have multiple pages with some metadata before it. So a page is the smallest unit of storage in Parquet, and it has a certain number of values. And this is encoded and compressed. So if we look inside a page, what we have, you will have a header followed by the repetition and definition levels. And so this is a small overhead that contains the information if the data is nested or is nullable, or where the nulls are, where are the lists starting. And then you have all the values. So it would be the same thing at flattening all the values for that column and storing them one after the other. And then you have extra information to figure out where the nulls are, or which values are part of what list if the data is repeated. And the way we store, so to simplify, you can consider this definition level as just being 0 and 1s to say whether a value is defined or null. And so we encode that. We have a hybrid encoding, and there are two modes to it. One is very simple. It's run length encoding. And run length encoding is if you have many times the same value. Let's say it's all defined or it's all null. You will have a lot of zeros or a lot of 1. We have a very simple encoding that says we have that many ones, right? You store how many values you have and what the value is. And so, it's just very small. And if you have a lot of 0 and 1s interleaved, because it's kind of random which values are null and which values are defined, then we use bit packing to use only a single bit to store that information every time. And this is a little important because we'll go back to that on how you integrate Parquet and Arrow to make a very fast reader by peeling out those levels of abstraction. So if we look at Arrow, and it's slightly different in its representation. So like Parquet, it's well documented. The goal is to make a language agnostic in-memory representation. Whether you access it from C++ on Java, it doesn't matter, and you can use it to communicate between a Java or C++ process. But it's designed to take advantage of modern CPUs and get the maximum throughput out of it. And so that's the kind of thing you get through vectorized execution and using a columnar representation. It's embeddable, so usually it's not visible to the end user. It's what the execution engine is using under the hood to go faster and be interoperable with speed. And so it's embeddable and interoperable. So like Parquet, it supports nested data structure, and I will show an example to show it works. And it maximizes CPU throughput. So there are 3 main properties here that it optimizes for. One is pipelining, because processors don't execute instruction one after the other anymore. They're trying to pipeline. and to stagger execution and instructions. SIMD is single instruction, multiple data. And similarly, modern processors will have operators that can execute on multiple values at a time. So you can say, do that same instruction on those 4 values in parallel, and you get 4 times the same throughput when you do that. And when the data is columnar and you put all the values one after the other of the same type, it's really easy to use in this manner and say, hey, look, instead of doing a loop that's going to do 1 value at a time, it's going to do 4 values at a time or 8 values at a time and go that much faster. Cache locality is this other trick that processors do to go faster, because the CPU can process much faster than it can fetch data from main memory on the bus. It will have some local memory inside the processor that's much faster, but it's much smaller. So every now and then, it needs to fetch data from the main memory to put it in the cache. And this, of course, every time the CPU does that, it has to wait for this to happen. So you have big latency. The CPU waits, gets the data, keeps processing on what's local. And because the data is columnar and you focus on 1 column at a time, you get actually much better cache locality. Because when the data is row-oriented, remember, you have all the data for all the columns that are mixed together. And so you need to bring all the data at once. But when you have columnar representation and vectorized execution, you can focus on 1 column at a time. And you move a lot fewer data at the same time. And the last property is scatter-gather I/O. So this property that I alluded to earlier, then arrows representation in memory and on the wire to sensor the network is the same. And we'll see that in a subsequent slide. But it's the same representation. It's all relative offsets, and there's no pointer, absolute pointer to calculate. So you can just take the buffers from memory directly to disk or directly to the network and back to memory without having any transformation from the CPU happening, like you would have for Avro or for protocol buffers or those types of representation that requires turning absolute pointers into serialized representation. So this is the CPU pipelining I was talking about. So modern CPU, they split each instruction in multiple steps in a pipeline. So here, I imagine 4 steps in my pipeline. And so ideally, you start executing the first instruction, and as soon as the first step is finished, you start executing the second one, and so on, right? So as they process through the pipeline, everything is happening almost in parallel, right? But if there's any dependency between those instructions, you can actually not start the next instruction before you get the result of the previous one. For example, if there's branching, right? If you have an if statement, and depending on the result of the previous instruction, which is the test, you need to decide which next instruction you execute. And so that introduces bubbles, right? And because here the pipeline is 4 steps, but modern pipeline is more like a dozen of steps. And you lose that many cycles every time it's happening. So that's where the CPU is trying to be smart, and as his branch prediction algorithm, when anyway, if he doesn't know, it would have to wait. So he's going to guess. You have a branch, you have an if statement, and you do either that or that. So he's going to pick one and start executing that. And so that's another property where, and that will be important in the way you implement your reader to go faster. So this is the arrow representation. So if you have fixed width values, it's simple. You just put one after the other in a vector. So here, age, 18, 37, you just put 2 values one after the other. If it's a variable length values, like a name, you put all the values one after the other, and you have an extra offset vectors that point to the beginning of each value. And this is composable. For example, if I have a list of variable width values here, I put all the values after one another, like this value, this value, this value, and then there's an offset vector to point at the beginning of each value, like the first phone number, the second phone number and the third one, and so on. And there's another offset vector to point at the beginning of each list. So it's composable. So that's how you deal with nested data structures in a simple way. And then when it goes on the network, you can just have a simple data header that points at each of the buffers, and then you put each vector one after the other. And because those offsets are all relative to the beginning of the buffer, then it's relocatable, and so you can copy it to the network and back to memory, and you don't need any transformation. So now, if we take advantage of understanding how those things work to do a better reader for Parquet into Arrow, so if we take this simple example data, so let's say this would be the JSON representation, A, B, third value is null, then there's C, and then a null value and D. In Parquet and Arrow, really the main difference, in Parquet we put all the values next to each other, and we encode and compress them together. And then we use the definition level, which for a flat representation is really as simple as 0 means null and 1 means define. And we store that. And we try to be compact. In Arrow, to enable random access, we actually leave empty slots for null values, right? It's just, this value is just undefined. There's a slot in this vector. It's not used. We know because there's a 0 here. We don't try to read it. It's null. But that way, we get constant access to access any of the values. And you have a bit vector that says if it's defined or not. So a simple way to do reading Parquet into Arrow is, well, you iterate on all of the values. If the definition level is 1, that means it's defined, and that means we set it in the right slot. And then there's a bit vector, so every time we set it, we need to get the byte that contains that bit, figure out which bit to set, so we use a mask to set it, and then set it back. So that's how you set a single bit in a byte, right? So there's some abstraction, and if you remember what I told when I said about pipelining, right in the middle of that for loop, we have a big data-dependent if. So that's really bad for the branch prediction for pipelining. Because that means the branch prediction will be often wrong because it's kind of random where the nulls are. And so you're going to spend a lot of time just waiting for that pipeline to flush and start over. So you don't, and it's actually huge things, right? Because you can lose, every time there's a misprediction, you lose 10 cycles. So you can go 10 times as slow just because of that. So instead, software is like augers, it's like onions. It has layers, right? So layers of abstractions are good because that help us understanding stuff. But in that case, really, we want to peel away those abstraction layers and understand better. Instead of just iterating on the thing, we need to understand how they are encoded. And that's why it was important to follow the other slides. I hope you did. And look at, wait a minute. We have actually two cases, if you remember. One is you bit pack once, 0 and once, and you need to figure out where to put those values. And the other one is run length encoding. So let's look at the bit packing case to start with. So the main difference with this implementation in 2 steps is it removes the if statement in the middle. So first, we can look at the definition level. Remember, it's 0 or 1. And figure out the index of each non-null value. So if you have a simple running index of what the current index of the value, if the value is null, then it's not put in a slot, so there's not going to be a value in Parquet. So we can just increment by 1, and then we can just set this value of keeping the non-null indexed. So values that are non-null will maybe set more than once, but the advantage of this loop is there's no if inside of it, right? It's just doing the same thing over and over. And so it's going to be very fast from the pipelining perspective. It's going to take advantage of the full throughput of the CPU. There's no if statement in there. It's a very tight loop. The disadvantage is we have to materialize those indices, but we're hoping that the extra instructions is negligible compared to the throughput gain of not having a branch misprediction. And then you can just decode the values and put the value in the right index, right? So we added this figuring out those indices, and it's much faster. And the other case, when it's run length encoding, so no branch, and the other case is actually even better. So if in your data you actually don't have any nulls, then you can remove entirely the overhead of dealing with nulls, right? Because now, if we don't have any nulls, we're going to have, say, hey, look, we have, here I have 4, but it could be 10,000 once, right? It's just always defined. So you can fall back to that case where, look, it's all defined. We don't deal with nulls anymore. We know all the values are next to each other. We can just write them where they are. And in the case it's null, well, look, we have 10,000 null values. There's really nothing to do. We're just going to increment our index by 10,000, and we're done. Instead of doing a loop that has this abstraction, when we read every value through the abstraction, that returns 1 10,000 times, and then 0 10,000 times, and do nothing. And so just by peeling away those abstraction layers, we can do much faster and actually fall back to the case where we didn't deal with null at all. So that's for the simple reader. Now the next important part is predicate pushdown. How do you make those filter evaluation, because you integrate tightly the top level, which is execution, with the bottom level, which is reading from the storage layer, you can actually be much faster. So if we take that example, so remember that Parquet file, and let's assume we have 4 columns in it, A, B, C, D, color-coded it to make it a little easier. And let's say you select B, C, D, and you have a filter on A, right? So you're going to keep the lines in B, C, D only when A matches the filter. So the simple version is, well, you know, we have those pages that contain data, and we can decode the values, load them in vectors, and then we apply the filter, and we keep, so I said where A equals 3, I have in bold here the rows that match this filter, and we keep only the values that we're interested in, right? That's simple. But actually, we can do much better because we understand this better. So if we do, again, we peel away the abstraction, and we do more lazy, what's some system called lazy evaluation. You can first evaluate the filter. So you can take A, and actually every of those header here for each page has stats. It knows the minimum value and the maximum value in this page. So since you want to filter out where A equals 3, you know, if the min and max tell you that, you know, if the min is 5, you know it's not going to be any value in there. You can skip reading that page. You can skip decompressing that page. You can skip decoding that page. And so you can, you know, here I'm assuming I'm keeping only one page from the ones I have based on the stats, especially if the data is sorted. If you sorted on the column A first, it's going to drop down to a lot fewer pages. And then we can decode the values that are left and evaluate the filter. And instead of evaluating the filter and directly, you know, on the whole decoding things, you can first evaluate the filter. And here we store the deltas instead. So for example, we have the first value matching. So that means we have a 0 here, which is how many values we skip to get there. So we keep the first value, we store 0. And then we skip one row, right? This value doesn't match. So we put a 1 to say we skip one row, and then we get the next one. So you have as many values in the deltas, that rows that have matched, but you keep track of how many rows you skipped in between, right? And the advantage of that is you can take the other column and reapply those deltas to select the values that match, right? Because once we evaluated the filter on the first column, we can select the values that match in the other column. But again, because in each page we know how many values there are, if the delta skips all the value in the page, then we can skip the entire page altogether, right? We don't need to decode it. We don't need to decompress it. There's a lot of CPU saved. And also, depending on the encoding, if it's a fixed width encoding, skipping values says that you don't have to decode intermediate values to get to the next one, right? You can just skip that number of bytes. And depending on the encoding, you can take a lot of advantage. So you can use first, skip the pages that anyway didn't have anything. So we skipped entirely the second page, so there was nothing after a certain number. we can skip all the pages that have rows after the last one that matched. And then when we decode, we just apply the deltas to get the next data. And so you get a much faster, you skip a lot of decompression and decoding by just understanding the abstraction layers and going through them. So this, all this is not yet open source. It's work we've been doing, and that's going to, it was supposed to be open source for this presentation, but it's going to be over the summer. And so you're going to see that soon. Now I'm going to talk about things, so we're talking about that roadmap, things that are design is in progress, and people are welcome to join. So the other things that, so one thing that Arrow brings, and that this first part was about, is speed, right? We do vectorized execution, we can make things much faster, and we can have this vectorized reader that's going to be standard for a bunch of those things. Now the second thing is also make it a standard, right? So for example, there's work that is happening in Spark, and it's making the whole PySpark integration faster. So there's a lot of overhead in the existing PySpark in converting between the JVM-based representation that Spark uses to the Python representation to work on, to write UDFs. And this adds a lot of overhead. And so switching to arrow-based representation makes it much faster because now there's no CPU spent serializing and deserializing. The representation is the same, so you can just write arrow on the Spark side, send the record batch over to the Python process, and one is running on the JVM, the other one is a native process. The Python code, a lot of work has been done on the pandas side to work directly on top of Arrow. So it works directly on top of Arrow, so it doesn't need to convert it to Python objects like the PySpark, existing PySpark does. And it's much more efficient. So in this representation, you can imagine SQL engine. So it could be, Spark SQL, could be, so for now there's Spark integration, but in the future, you'll have Impala, Drill, Presto integration. And the next step is to use shared memory to remove the cost as well to serialize, deserialize, to copy those buffers. So we don't have the cost of serializing, deserializing because it's the same representation, but we're still copying the buffer for now. So in the future, you can use shared memory. And because it's the same representation, you can just have a read-only pointer on this. And read your input, cross-process, write your output, and then share it back to give it back to the SQL engine. So let's say, you could be using Drill with a Python UDF. And the advantage of this is because this representation is standard, now your library of user-defined function is portable across the SQL engine. You don't have to write UDFs for Hive, you don't have to write UDFs for Impala, UDFs for Drill, or for Spark SQL. Right now, and maybe you like Python, maybe you like Spark, now all those UDFs are portable across things, and there's no cost of, a lot of work is spent like making sure when Impala calls UDFs defined in Java, they spend a lot of time making sure they don't spend too much cost doing the conversion between native code and Java code. And so this standardizes it, and so we can combine all those efforts and do it once, and do it well, and do it very efficiently. So that's one example of communication, using user-defined function. And the other one is inter-process RPC communication, right? You can define a generic way of retrieving data in arrow format, a generic way to serve data, and simplify the integration across the Arrow ecosystem. It's really just an Arrow pipe, and we can send data from one process to another in string fashion or in batch, and that would work. So one example is how you would retrieve data in parallel for data storage layers. So imagine you can either have Parquet files on UDFS or Hedge-based Cassandra or Kudu cluster. And the main thing is to be able to read this data in parallel, right? So it has its own storage, and Kudu is columnar, Parquet is columnar, so Kudu can do the same fast read directly into columns that can be really fast because it's vectorized is one column at a time. And then serve it directly to the next layer, and it's directly there in-memory representation. So you remove all the overhead of converting. Today, Kudu serves a row-oriented representation. It has a columnar representation, and then it will assemble into rows, so there's some cost to that. Because most interfaces that are understood today are row-oriented, and then a query engine like Drill, for example, will turn it back into column in memory for its fast execution. So it's kind of nonsensible, doesn't make any sense that we turn columns into rows back into columns just because that's the common way to do it today, right? Really, it's all we need is to move to that standard. So that's this effort, is to have this standard columnar representation to avoid this. So similarly, you can do a row-based cache, and that's how you would do query execution. And so Drill, for example, does something similar with row-based execution reading Parquet. And so you have this part, which is the vectorized read in a fast way like I was presenting in the first part. And then when you do partial aggregation, you do partial aggregation based on how many machines you have on the second hand that do the final aggregation. So you prepare the input for each of the next step on each, and then they send it to each machine based on consistent hashing. And then final aggregation is done here, and then you send the final result to the user. So you can set that up as all those are streams of data that are sent from one machine to the other, and using the arrow representation. So if you're interested in the current results, there's a lot of performance results. Wes McKinney wrote a lot of those blog posts. He's been doing a lot of investment on the Python side. He's a Pandas creator. So you have a lot of numbers on performance gain from that end. We already have a lot of language bindings. So Parquet, it works in Java, C++, and there's Python and Pandas integration that also combines with Arrow. There are many engine integration today. It's like faster to list the ones that do not support Parquet today. Arrow is much younger, but it already has a lot of language bindings. So Java, C++ are the main one. On top of the C++ one, you have Python, R, Ruby. There's a plain JavaScript implementation. And engine integration has started. And so it makes sense to keep going and doing the integration. To give a sense of activity, so we started a year ago, a little less than a year ago. At the beginning, there was agreeing on the metadata and the format. And you can see that you were trying to accelerate. So orange is number of days. So to do the release more and more often. So now we're trying to do once a month. And so there have been a lot of changes, a lot of activities, and it's settling. And now we have the format is pretty much finalized, and we get in that phase where we want to integrate with a lot of things. And so there will be small changes more often, and all those integrations are happening in parallel. So current activity, if you're interested, you can follow the Spark integration as a saying activity, and there's going to be multiple follow-up steps on that to integrate it deeper and deeper. There are a lot of discussions currently happening to add the pages index in the Parquet footer, so those push downs make them even more efficient, right? So we want to be able to skip reading the pages altogether. So you want to do as much as possible filter evaluation on the statistics, mismatch for each page, so that you can skip reading a lot of stuff, and then do a deep integration in the filter evaluation, so that you can make it very efficient. So if you're filtering a lot of stuff and your data is sorted, for example, then it's going to be that much faster because you're going to be able to pinpoint exactly where in the files you need to read. The Arrow REST API is being defined, so if you want to chime in on this ticket, all the metadata is defined. It's just about how do we define the encapsulation for those messages. There's bindings are making progress as well. There are some people that are very interested into having a JavaScript implementation so that you can have a backend that serves Arrow, and they can do a lot of computation in the browser. Browsers now, I've seen demos where people do things with tens of millions of rows of values in the browser and doing computation on that. The only thing is you don't want to represent it as JavaScript objects because you blow up your memory. You want a much better representation like Arrow, and you can actually do a lot of visualization and fast computation based on that. So if you want to get involved, mailing lists, it's an Apache project. Contributions are always welcome. They're not required. You're welcome whether you have questions, you have suggestions, you want to contribute. We have Slack channels for more interactive discussions. We have mailing list if you have questions, if you want to be oriented. Contribution are welcome. Don't feel like you don't know, you're not sure if you're allowed to contribute. Of course you are allowed to contribute, and don't hesitate. And if you want to help with something, and like I was saying, we're in that phase where integration with multiple things can happen in parallel, right? So if you have a pet project and you think it's moving too slow on that end, if you want to help with this, you're very welcome. And that's it. And I think, do we have time for questions? Hey, if nobody stops me, I can speak forever, right? Okay, well, yeah, go ahead. Yes, so usually in Parquet and Arrow schema evolution, so Arrow has some special type. It has a union type to deal with, your type used to be a string and now it's an int. And so there's the schema, the type definition support that, and you can do things like that. And sorry, that's the last question. I'm going to be outside to answer more questions if you want, but I have to leave the room for the next speaker.